Okay, in this video, we will go over address ranges, and the objective here is that to be able to calculate the range for different types of memory that you might have in your system. Sometimes a system will have like a RAM, ROM, input and output, etc., peripherals and whatnot, and those reside at different locations in terms of the address space. And it's a good idea to actually understand the starting address and the ending address for each type of component or memory in your system. Eventually, we will use this as well to kind of help us with designing the memory address range and the address decoding for the memory, which we will basically put together like a complete example at the end. But for now, let's try and understand how to do or calculate the address ranges. So let's take a look at an example here. I have a memory system that's composed of ROM and RAM, and they are back-to-back, and they start at address 0 hex or 0000 hex. And the question or the objective is to figure out the range for each of these memory types. Okay, so let's assume the memory is starting with the ROM, and it's starting at address 0. And it occupies 64 spaces, assuming each space is holding 1 byte. So I need to go up to 64. Now, you know from binary counting that 64 is 2 to the power of 6. So your first instinct would be to go and say 2 to the power of 6 will be, this is 0, 0, 0, 0, that's 0, 1, 2, 3, 4, 5, 6. And that would be my 2 to the power of 6. But if you do it this way, you're essentially saying that I'm starting at 0 and ending at 64, starting from 0 going to 64. That's actually 65 locations. So we're one address extra than what we need, because we're counting from 0. To give you an example, again, on the side, before I keep going, if you have 3 bits, you go 0, 0, 0, 0, and then the last address is 1, 1, 1. So this is 0 in decimal, and this is 7 in decimal. Obviously, the value we end with is 7. However, there are 8 different combinations, right? Because we're starting the count from 0. So it's actually 0, 1, 2, 3, 4, 5, 6, 7. So that's 8. So similarly here, we don't want to go all the way up to the value of 64. We need to go to 63. And counting from 0 to 63, that will give us 64 location. So if I use that logic, I need to actually stop at address 63. So all I have to do is actually subtract 1 from this range. So if I subtract 1 from that, like this, I end up with 1, 1, 1, 1, 1, 1, 0. Okay, that makes sense. So the ending address becomes 1111, 110. This is bring down the remaining zeros. 0, 0, 0, 0, 0, 0, 0, 0. This is the ending address for the ROM. Before I keep going and to the RAM, maybe then here we have a shortcut, a trick to actually calculate the ending address rather quickly. I noticed that I actually ended up with 6 ones, because 2 to the power of 6 is 64. So going forward, when I have a memory that starts at address 0, what I can do is I just flip the number of bits that correspond to, or they're equal to, the number of the power, or the value of the power of 2. So in other words, let me erase those one more time. So we want to go to address 63, because that's my ending address. So, and we said 64 is to the power of 6. So I'm just going to write 6 ones here. 1, 2, 3, 4, 5, 6. Then these 2 bits are still 0. These 4 bits are 0. And then these 4 bits are also 0. And then that is the range. So the starting address of the ROM is 0x 0000, and the ending address is 0x 00. And then these 2 ones, sorry, these 2 ones are 3. and then the last four ones are F. So the ROM address space is between 0000 to 003F. And because the memories in this case are residing back to back, so the RAM here is going to start at the next address immediately after 003F, and that's going to be 0040, right? So if you add 1 to that address, what do you get? You get 0000010. Again, these bits are 0, right? And where does it end? The same exact logic applies as well. Because it's 64 byte, I have to flip 6 ones, the lowest order 6 bits. So 1, 1, 1, 1, 6, like that. So the RAM address range is then 0x0040 to 0x007F. Let's take a look at another example here. We have 128 byte of ROM, followed by 128 byte of RAM, followed by 16 locations for input and output back to back, starting at address 0000. So I'll do the same logic here. We're starting with the ROM, and it occupies 128 bytes. So that means, so I ask myself, 128, that's 2 to the power of 7. So a quick way to do this is, like we said, we flip 7 bits from 0 to 1, the lowest 7 bits. So this will be 1, 1, 1, 1. That's 4, 5, 6, 7. The remaining bits continue to be 0. So the ROM range then is from 0x0000 to 0x007F. The RAM will start immediately after that. So if I add 1 to this range right here, I end up with 1, 0, 0, 0, 0, 0, 0, 0. Then those are also zeros. And then the RAM is also 128 bytes or 128 locations. Each location is holding 1 byte. So I also flip those bits to 1. So I have now okay, so the RAM is starting from address 0x0080, and it ends with 0x00FF. So this is my RAM. Now the I/O, like we said, is 16 locations starting after the RAM. So if I add 1 to this, I end up with 1 here. 1, 2, 3, 4, 1, 2, 3, 4. Then the remaining bits are 0. Okay, and 16 locations or 16 addresses, that's 2 to the power of 4. So we flip these bits, 1, 2, 3, 4. Then okay, so my I/O in this case is starting from 0x0100 to 0x010F. This is my I/O range. Hopefully now you can see that, how we're doing. So this is basically the address range for different types of components in the system. And if you like, or if you're using like, for example, if you want to see this like in real scenario, you can look at an actual system. Sometimes like maybe in Microsoft Windows, you can look at resources connection by address ranges, and you'll see like this kind of numbers in a system, and that will tell you where is each location or resource at what each where is the resource that you have located in the address space. Anyway, this is it for this short video. We'll do one more with an example on how to use this for our memory address decoding.